So I'm Sajid Fardin Dipto, and I'm a PhD student uh, at George Mason University. And the title of my presentation is Covert Channel Risks in Biomedical Systems, ACMG signal exfiltration, and speech reconstruction threats in clinical networks. So at first, we need to know what is ACMG data. So ACMG stands for surface electromyography, and electromyography or EMG data. This is a medical test data that records electrical activity produced by our muscles. So when a muscle contracts, it generates tiny electrical signals, and surface EMG is the non-invasive version of this technology. So instead of inserting needles into our muscles, we place our electrodes on the skin to detect, amplify, and record the electrical activity. So ACMG is generated by our muscles. And what makes this particularly relevant to our discussion is how this technology is being used in hospitals or clinics. So like outpatient voice or swallowing clinics treat dysphagia and laryngectomy, and also who have had their voice box removed and various hyperfunctional voice disorders. So let's talk about the problem. The core issue is that biomedical rehabilitation systems who use ACMG sensors are unintentionally creating some covert channels for data exfiltration. So first of all, the EMG devices are increasingly connected to hospital networks. And secondly, uh, raw ACMG data can be used to reconstruct private conversations. And thirdly, we can say that many of these medical devices are designed without security for biosignals in their mind. Uh, so let's talk about why the problem matters. So ACMG devices capture muscle activity patterns that actually encode speech. So if these signals are leaked, uh, an attacker could potentially reconstruct the voice and the actual content what was said. So this isn't just a privacy violation; it's a complete exposure of potentially sensitive patient conversation. And obviously, there are multiple stakeholders like patients, clinicians, hospitals, and there's something what makes this urgent, and that is the machine learning models capable of converting this SEMG data. These signals can be converted into speech and using these machine learning models. And these models or data set are publicly available right now. So uh, if I want to talk about from an engineering perspective, this touches all the critical pillars we care about, that is safety, privacy, security, and resilience. So why should hospitals must care? So there's regulatory risk. Any breach involving patient data could result in HIPAA violation. And secondly, there's operational risk. And from an ethical perspective, healthcare fundamentally depends on patient trust and informed consent. So if patients discover that their private conversation during therapy could be reconstructed from their medical data, that trust actually violates. So there are some prior works. Dr. Getty demonstrated that EMG signals can be mapped to speech reconstruction. And on the clinical side, many of the hospitals or clinics like John Hopkins Medicine, they use ACMG regularly for therapy. Uh, so, uh, so where current solutions fall short. So first of all, there are no established risk models that treat biosignals as speech proxies. Like uh, this does not come into their mind that these type of biosignals can be converted into speech. And secondly, there's lack of um, security or privacy modeling and in biomedical signal pipelines. And also the rapid advancement in artificial intelligence and also deep learning has made this threat uh, made this threat immediate. And so what was theoretically possible a few years ago is now practically achievable nowadays. So in case of threat modeling, I designed a data flow diagram with considering the sprite model. So here, a person can impersonate the sensor or workstations that's spoofing, and an attacker can modify EMG signals that's tampering, and there's also unauthorized access. But the most important thing is the information disclosure. So this is our actually primary concern in this research. So the speech reconstruction attacks can expose private conversations. And also we have denial of service and elevation of privilege, which are not that important. So we analyzed across the systems Bluetooth and Wi-Fi transmission, the hospital database, data export, cloud storage, and maintenance operations. So these are the attack points. So if we look at the data flow diagram for EMG system, we can see that we have the patient environment in the left side. So here the EMG data are collected through some devices, and those data can be sent through a Bluetooth or Wi-Fi data transmission, and we apply some signal processing or visualization in with that signals with the EMG signals, and after that, those signals can be stored in hospital database, and also clinicians can export those data for their use or for therapy or for analysis, and these data can be also stored on the cloud. And also this data can be sent to some research institution for research. So here we can see that to some points like the Bluetooth or Wi-Fi transmission or the database storage or the cloud storage. So these are the attack points of an attacker where the attacker can actually where the attacker can actually acquire the EMG data and they can actually convert them into speech. So let's talk about now the data set. So we used actually the data set from Dr. Gary, uh, and the total data, the total EMG data was 3.6 hours, and the vocal data was that's the audio that is 15.1 hours, and the average utterance has 16 words, and there are almost 10,000 words in that whole vocabulary. So in the image, we can see that the electrode positions through which the EMG data can be collected. So these are the positions where the electrodes are placed. And in the right side, we can see the EMG data plots. And we can see that here there are variations in EMG data. And on the right bottom, we can see that for the specific corresponding audio data for that EMG signal. So let's talk about now the speech reconstruction attack model, which is my main research focus. So I developed a deep learning model that can reconstruct speech from EMG signals. So this model actually uses an architecture which combines convolutional neural network for feature extraction and also transformer architecture with Lyapunov regularization, which is a non-linear regularization. And we actually start with 8 channels because there are 8 electrodes, and those are sampling with 1000 hertz. And also these residual CNN blocks extract those features, those muscle features, and these convolution layers actually learn to identify the patterns in EMG data. So next we have transformer encoder, which captures the temporal speech patterns. So uh, finally, after transformer, we use dynamic time warping to align the silent EMG recordings and vocalized speech because uh, the silent data and the vocalized data are recorded on different sessions. So they have mismatch on time series. So if so, uh, this is my model architecture. So in the left side, this is the total deep learning model, where we can see that the EMG signals are sent into the convolution feature extraction for extracting the features, and they have 768 dimensions. And the extracted features go into a transformer encoder layer with 6 layers, and each transformer layer has 8 attention heads, and it has also a dimension of 768. So the transformer is actually particularly uh, good at capturing long-range temporal dependencies, as we know. And here we used 3 losses, the dynamic time warping losses for time series mismatch alignment. And we have also phoneme loss for auxiliary learning. And we also have the Lyapunov exponent regularization, from which we calculate the Lyapunov loss. So Lyapunov loss is a novel contribution in this work because it helps temporal stability, and it helps to capture chaotic properties of the predicted audio. So also it encourages the model to learn dynamically stable speech consistency and natural vocalized audio. So we have the predicted features, so which is represented by male frequency septal coefficient. And we have also the septal coefficients from the target audio. So we minimize these losses. And after that, we send these predicted features into the hi-fi GAN vocoder, and we generate the speech. And in the right side, we can see that the convolution feature extraction block, where I have used 2 convolution blocks in the forward network and a residual connection also. And this is actually my architecture. So let's talk about the speech reconstruction performance. So my proposed model achieves a word error rate of 32.22%, where Dr. Gaddy, the baseline model, achieved 42.20%. And this is the common matrix which is used to measure the quality of the generated audio, which is word error rate, where S, D, and I are the numbers of substitution, deletions, and insertions. And N is the reference transcript length, or the total number of words. So we can see that our proposed model, improved by 23.7% relative error reduction. So if we want to visualize, the top signal represents the ground truth audio, and the bottom signal is the generated audio, reconstructed audio. So we can see that these are very similar, and the overall structure we can see is preserved. And for audio samples, we can actually listen that we cannot tell the difference, that they are the one is ground truth audio and the other one is reconstructed. So if I play this, so this is the ground truth audio, and from EMG data, I have actually reconstructed the same audio.
We
can see that
we cannot hear. Can you share? You need to share with the audio.
Okay.
If you can reshare, you can see and share with the audio, please.
Yeah, okay. So for the ground truth audio, if I play this,
I myself heard nothing of that.
And if I play the reconstructed audio,
I myself heard nothing of that.
So the reconstructed audio is generated from EMG data, so we cannot actually tell the difference. Those are the same. So yeah.
I myself heard.
So about the privacy implications, this level of accuracy, that is almost 32% of accuracy the word error rate means that out of 3 words, 2 are actually transcribed correctly. And also, it is actually sufficient for any kind of command recognition or keyword extraction. And also, we saw that actually we can reconstruct silent or subvocal speech. And with the help of latest hardware and the latest deep learning models, we can actually um, achieve more better results. So for this reason, SEMG must be treated as high sensitivity data, the biometric data. So there are some um, mitigation suggested uh, by searching. So actually, we can uh, as we see that the EMG data can be transferred through Bluetooth or Wi-Fi. So for Bluetooth lower energy connections, the system can actually use LE secure connections with authenticated pairing. So this actually means that both the sensor and the receiving device verify each other's identity before exchanging any data. Also, hospitals can use device unique keys rather than shared keys and implement periodic key rotation uh, for secure transmission. And for Wi-Fi security, they can use TLS 1.3. Um, and we can also implement certificate pinning to prevent man-in-the-middle attacks. And in case of authentication of medical sensors, we can actually use the efficient, strong authentication protocol, that is ESAP, for the medical sensors. And uh, the last of all, proper key management actually is critical. We can implement periodic key rotation, as I have mentioned earlier. And this is for the mitigation of secure transmission. And in case of access control and database protection from the data flow diagram, the role-based access control with clearly defined roles for clinicians, researchers, administrators, we can actually uh, control the access. And in case of SQL injection on the database, we can use something like object relational mappers. This can prevent attackers from injecting malicious SQL commands. And in case of encryption at rest, we can use advanced encryption standard with hardware-backed key management. This actually can help um, to remove or this means actually if someone physically steals a hard drive or database backup, they cannot actually read the EMG data without the encryption keys. And also the admin controls, we can actually implement privileged access management that requires dual approval for high risk operation. And through this, we can actually implement this. And in case of data export and cloud security, for cloud encryption, all files can be encrypted with a strong symmetric encryption before network transmission. And finally, for secure channels use mutual authentication, meaning both hospital system and the cloud provider, they verify each other's identity. And we can use signed URLs with time-limited access tokens to actually prevent unauthorized access to cloud storage. So we have actually limitation, and there are some future work directions. So first of all, my work relies on existing EMG dataset collected in a controlled research setting. So in case of real-world clinical environments, those environments can be noisy. So there can be electromagnetic interference, and there can be electrode placement mismatch. So yeah, performance and risk assessment may change in the real-life scenario. And for that reason, future work should validate this research on physical test beds with actual medical devices in real-time clinical settings. And we need to also consider the privacy and security real-time concerns. And we need to also measure the covert channel bandwidth under some realistic conditions with real patients. So in conclusion, mm, we can say that biosignals are not just clinical measurements. So they are high-value communication media that require actually rigorous cybersecurity engineering. And the convergence of biomedical sensing and AI has created a new class of privacy threat that the security community must address. So these are the references used for this presentation. Thank you very much. If you have any questions, you can ask.